After studying this module, you shall be able to know the potential energy curve for various approach angles, carry out trajectory calculation, know the relative velocities, find out reaction probabilities of reaction. Introduction. On obtaining the potential energy curve for various approach angles theta using time-dependent Schrödinger equation, the probability of a reaction to take place for certain initial conditions can be found out. Since this type of calculation have numerous difficulties, therefore theoricists instead use the classical mechanical approach. We know that the force on the particular nucleus is given by the negative gradient of the potential energy gives the force applied on the nucleus. Therefore, for example, the component of the force in the x direction of motion on nucleus I is given by F is equals to minus del V by del xi, where V is the potential energy and xi is the x coordinate of the nucleus. At each instant, the system can be represented by a point on the surface, and thus Newton's second law of motion, that is F is equals to m into a, is integrated numerically to get the coordinates of the system as a function of time. Calculations can also be done when HBHC originally has vibrational motion, and this is treated classically as an approximation. Rotational motion can be neglected in such calculation. For the fixed initial conditions and L for others, the reaction probability comes out to be 0 when the trajectory calculations are carried out. For the collinear collision, the outcome is represented in figure. The molecule HBHC is vibrating in figure A and HA approaches with a fixed initial velocity, but the reaction does not take place. It is observed that the collision is inelastic and is non-reactive. As a result, the translation energy only gets converted into vibrational energy in the HBHC molecule. There is no reaction taking place in figure B also. You can see in figure A the trajectory of a non-reactive inelastic collision of a hydrogen atom and a hydrogen molecule. In figure B, the trajectory for a reactive collision is shown. For carrying out calculations in this manner, it is important to execute a very large number of trajectory calculations with initial states decided to provide a acceptably representative sample of possible initial conditions that can be decided by a Monte Carlo way to make sure that the distribution of each initial parameter approaches the correct distribution as the number of calculated trajectories increases. The relative kinetic energies of HA and HBHC can be calculated by the Boltzmann equation. All angles theta of approach are to be included. However, it has been observed that most reactive collisions take place at an angle close to 180 degree. The cross section sigma of the reaction is given by equation 1. In case of bulk chemical reactions, molecule may collide with different relative velocities, and hence the rate constant kT at temperature T consists of the sum of the terms for all the possible relative velocities, each term being weighted by the fraction Fi of collision with the corresponding relative velocities. It is given in equation 2 and 3, where F is the Maxwell-Boltzmann distribution for relative velocity V at temperature T. In 1965, M. Karplus, R. N. Porter and R. D. Sharma found a large number of trajectories for H plus H2 reaction and observed that their results could be written in the form of following Arrhenius type equation, which is shown in equation 4. The theoretical results match very well with the experimental results calculated for the reaction D plus H2 giving DH plus H, or H plus para H2 giving ortho H2 plus H, shown in equation 6. And with the value find out utilizing the activated complex theory over the same temperature range can be calculated as given in equation 7. For the assessment of the rate constant from a series of trajectory calculation, we need to assume the reaction probability Pb, also called opacity function, and the reaction cross section sigma v can be found from this method. The reaction probability Pb is equal to the ratio of the total number of trajectories at a particular relative reactant velocity and the impact parameter B that result in reaction. For the reaction H plus H2, the reaction probability is indicated in figure for a given relative velocity of 1.17 into 10 to the power of 6 centimeter per second as a function of impact parameter B. The reaction probability is highest for B is equals to 0, reducing to 0 at some finite value of B. Hence, it can be shown that the classical calculation carried on number of simple reactions provide a satisfactory explanation for the collision dynamics of these reactions. The quantum mechanical tunneling, that is, penetration into classically forbidden region, may also become important at low temperature. Figure 3 shows a symmetrical potential energy diagram for the reaction HA plus HBHC giving HAHB plus HC. Though this is not usually true, the potential energy surface diagram actually indicates if translation motion or vibration motion will be more effective in carrying out the reaction. It can be observed that the reaction starts at the right hand side of each diagram and continues from right to left. It is necessary to find out the difference between the potential energy surfaces with early barriers and late barriers. Figure A indicates a potential energy surface diagram with an early barrier and a reactant with that much enough translation energy to cross the saddle point into the trough for the formation of products. Figure B indicates a potential energy surface diagram with an early barrier and a reactant with vibrational energy. Although the overall energy can be same as in A, the reactant might be bounced back from the barrier. Therefore, it can be concluded that an early barrier pushes the reactant with translation energy and produces vibrationally excited products. Figure C, on the other hand, shows a potential energy diagram surface with a late barrier and a reactant with vibrational energy. The wall of the valley may reflect the molecule through the saddle point back into the reactant valley where it may not have a considerable vibrational energy. Figure B indicates that a reactant may be reflected back in the reactant valley if it does not possess vibrational energy. Therefore, a late barrier favors a reactant with vibrational energy and yields a product with less vibrational energy. In addition, a potential energy surface that has an early barrier in one direction has a late barrier in the other direction. Let us understand in detail. In figure A, a potential energy surface with an early barrier and a reactant with sufficient translation energy to cross the saddle point is shown. In figure B, a potential energy surface with an early barrier and a vibrationally excited reactant is shown. In figure C, a potential energy surface with a late barrier and a vibrationally excited reactant is shown. And in D, a potential energy surface with a late barrier and a reactant that has sufficient translation energy to reach the saddle point but does not has been shown. Now let us summarize. The potential energy curve for various approach angle can be obtained using time-dependent Schrödinger equation. These trajectory calculations produce a reaction probability of 0 for fixed initial conditions and L for others. For carrying out calculations, it is important to perform a very large number of trajectory calculations with initial states decided to provide a acceptability representative sample of possible initial conditions. In order to find out the rate constant, it can be accessed from a series of trajectory calculation. We require number of trajectories at a selected reactant relative velocity and the impact parameter B that results in reaction. The overall inference is that classical calculations executed on a number of simple reactions have proved to be satisfactory explanation of the collision dynamics of these reactions.